Welcome back to Honors Calculus. In this video, we're going to be studying the equations of lines. Previously, we have established the real number system in a more secure footing than what you have seen previously. And in this video, we're going to extend that idea I guess that doesn't quite all fit on the screen with my head there. So the rectangular coordinate plane, and again, rectangular in parentheses, there are multiple different coordinate planes. You're familiar with the idea of the coordinate plane already. We've got a vertical axis, which is generally labeled as the y-axis. We've got a horizontal axis that is generally labeled as the x-axis. And if we take a random point, it has an ordered pair representation, A comma B, where A is the position along the x-axis and B is the position along the y-axis. The place where the two axes cross each other is called the origin and has coordinates 0, 0. Nothing new, nothing crazy going on there. Something you may be a little bit less familiar with is the notation. The set of all points in the coordinate plane is labeled as the blackboard bold R symbol we use for the real numbers raised to the second power. And it is defined as the set of all ordered pairs xy such that x and y are real numbers. An equation in two variables. Here we get to another hand-wavy kind of definition. This is, you know it when you see it definition, unfortunately. An equation in two variables is a rule that asserts that expressions which contain x and or y have the same value. A solution to an equation in two variables is an ordered pair which satisfies the equation. And the graph of an equation in two variables is the set of all solutions. In a full course on analytic geometry, we might specify some distinctions here. The solution set is the set of all solutions, and the graph is the depiction of the solution set in the coordinate plane. But that distinction is not important to us here. You'll also, in those contexts, hear people talk about the locus of points, which is another way of defining a graph without having to rely on an equation. But again, those sorts of discussions are counterproductive to our focus here in this course. So we're going to stick with this simplified definition. The graph is the set of all solutions, and we can visualize a graph by plotting these solutions on the coordinate plane. I started off today telling you that this lesson was on the equations of lines, so I guess we should get to that at some point here. The reason that I wasn't too concerned about the fact that our definition for an equation in two variables is very hand-waving is because there are going to be two specific types of equations in two variables that we spend a lot of time on in this course, and I can give much more precise definitions of each of those. The first one is a linear equation in two variables. A linear equation in two variables is any equation which can be written in the form ax plus by plus c equals 0, where a, b, and c are each constant parameters. A line is a line is the graph of a linear equation. And at first glance, nothing here should be surprising to you. But if you look a little bit closer, you may notice something subtly different about this definition than what you've seen in the past. You are, I'm certain, familiar with the fact that you can take a linear equation and you can graph it, and every time you graph it, you get a result that is a straight line. The surprising thing about this definition is that it's stated backwards. We are defining a line as the graph of a linear equation. That is what it means to be a line in analytic geometry. Of course, that seems to head against a definition of a line that you have heard in the past. In constructive geometry, the kind of geometry that is taught in high schools, you learn that a line is defined entirely by 2 points. Given any 2 points, there is exactly one line that passes through it. And in the geometry of Euclid, that was the definition of a line. So before we can do anything else, we need to make sure that these two definitions actually agree with each other. A line is defined entirely by 2 points. Given any 2 points, there is exactly one line passing through it. A line is the graph of a linear equation. That sounds like a theorem. Given 2 points, x0, y0, and x1, y1, there is exactly one line which contains both points. The equation of this line can be written as y minus y0 equals sum m times x minus x0, where m is defined as the ratio y1 minus y0 over x1 minus x0 and is called the slope of the line. Once again, you have seen slope in the past. You've probably spent an awful lot of time thinking about the slope of a line in the past. There are several ways you can define the slope of a line. It's generally defined graphically in a very interesting way. And that's something that we're going to be considering quite a bit later on in this course. But for right now, the slope is simply a notational convention. This y1 minus y0 over x1 minus x0 is going to arise naturally from trying to set up this equation, and hopefully something interesting can happen from giving this shorthand. That, again, is very often the way that mathematics arises. We come up with an idea that is a notational convenience, and then we investigate to see if that notational convenience has any application. Sometimes the first discoverer has the notation slightly wrong, and if the application is discovered soon enough, the notation changes. I'm quite certain that the idea of slope was first discovered geometrically and later came into algebraic, so this is not a good example. But there are certainly other applications, some of the things we'll be doing later in this course, where the notation came first, and then we found a way to make the notation useful, so we use a slightly different notation than what was first written by, say, Isaac Newton, who is generally credited as the discoverer of calculus. On the other hand, sometimes the notational convention takes hold a little bit too well before we discover the application, in which case we are stuck with terrible notation forever. The classic example of that is in the study of electronics, where Benjamin Franklin named the thing that moves around as having a positive charge and named the electron as having a negative charge at the same time. And if you've studied any electronics or electricity and magnetism whatsoever, you know that the positive charged protons pretty much stay in place and the negatively charged electrons move all over the place, making studying electronics a notational nightmare ever since, unfortunately. But that's not something that comes up in this course, just a cautionary tale of notation is sometimes invented well before the application is known. So you never know what the notation is going to actually do for you. All right. So let's take a look at this. Before I get started on the proof of this theorem, I want to point out, if I scroll up a little bit, that this equation of a line is not unique. Because that right-hand side is 0, if I multiply everything by 2 and get 2ax plus 2by plus 2c is equal to 0, I have the exact same linear equation, even though it looks different. And that's going to be something that makes this particular proof incredibly challenging unless we deal with it immediately. And so deal with it immediately we shall. We're going to deal with it by using a Woolog statement. I love Woolog statements because they let me get to say the word Woolog. Woolog stands for without loss of generality. It's a phrase that mathematicians use all the time for situations like this. We have 3 parameters in our linear equation, and we can multiply the equation by whatever we would like and still have the equivalent equation. For all practical purposes, it's the same equation, and we don't want to have to worry about that. So we're going to make a choice. I'm going to tell you right now before I scroll down and write it. The choice is going to be, let's assume that b is equal to -1. Because if we want to make b anything else, we can just multiply both sides of the equation by whatever that thing is. It will give us a new equation that is equivalent. Or put another way, pretend that we divide both sides of the equation by b, and then you get the -1 where it needs to be and everything works fine. So without loss of generality, Woolog, assume b equals -1. Now I can play a substitution game. I have ax minus y plus c is equal to 0. And I have the ability to substitute in my 2 known solutions. I know that x naught, y naught has to satisfy this equation. So I'm going to plug in x equals x naught, y equals y naught. I also know that x1, y1 has to satisfy this equation. So I'll plug in x equals x1, y equals y1. Now I have 2 equations. And I also have 2 unknowns, capital A and capital C. Given 2 equations and 2 unknowns, I should be able to solve these equations. And I'm going to do that by simple tack of let's subtract the second one from the first. I might end up regretting this. I think I might have wanted to set this up the other order. No, it'll be okay. And so I get a times x naught minus y naught. minus y naught, and then minus and minus is plus y1, and then I have plus c and minus c, which cancel each other out. So this is equal to 0. If I do some creative rearranging, I get this nice fraction. And since I had defined a fraction very similar to this earlier, notice that if I simply multiply top and bottom of this fraction by -1, it will change the direction of the subtraction. Like I said, I should have set this up with these two equations in the other order when I started writing it out, but that's not what I did. And that's the fraction we defined as m earlier on. All right. That may or may not feel very satisfying, but it does give us our result for A. And knowing our result for A, we can go back and try to figure out a value for C, which turns out to be fairly straightforward. Because our A is now little m times x minus y plus c is equal to 0. And if I plug in my choice either of the two points, but x naught, y naught is going to be a little bit more convenient, I get m times x naught minus y naught plus c is equal to 0, which means that c itself is y naught minus m times x naught. And with that, we now have that m times x minus y plus y naught minus m times x naught is equal to 0. We can rearrange this a little bit. M times x minus m times x naught is equal to y minus y naught, or y minus y naught is equal to m times x minus x naught. Again, many of you have seen this version of the equation of a line before. This is called the point-slope form of a line, and it is definitely the most useful tool for trying to write the equation of a line. And it turns out that writing the equation of a line is perhaps the single most important thing we're going to do in this course. We're going to write a lot of equations of a lot of lines. Before I move on, I want to point out a couple of things about this proof. First of all, I kind of assumed at the outset that our 2 points would satisfy a linear equation. In order to do that, if I scroll up the screen a little bit, hopefully I can fit that in and get my head out of the way. Yep, right there. In order to do that right here, I set up my b equals -1, and I noticed that I have an equation in two variables. One equation in two variables does not have a unique solution, but two equations in two variables does have a unique solution most of the time. There are a couple of exceptions that I didn't feel worth talking about. If x naught, y naught, and x1, y1 are the same point, then this equation is meaningless and we lose the there is a unique solution here. It was always possible that we came up with nonsense. Had we come up with nonsense, then we would be in a bit of trouble. To be technically correct, I probably should continue this proof from here. Now that we have this form and established that it is unique, we should prove that it actually does work for both points. Plug in x0, y0, plug in x1, y1, and show that in both cases you get a good solution. X0, y0 is pretty easy. X1, y1 takes a bit of work, but it's certainly possible. The other thing that I want to point out that is very definitely a flaw in this reasoning is this step right here. If you are looking at 2 points which are directly above each other, then x0 and x1 are the same, even if y0 and y1 are different. And that means that x0 minus x1 is 0, and we just divided by 0. So this equation for a line, the definition of slope, doesn't work in the case where you have 2 points that have the same x-coordinate. That gives you a vertical line, and that's something that we need to at least acknowledge. This proof just kind of ignores the existence of vertical lines. If you're really interested, I'm happy to spend some time going through it, but for the sake of time in this video, I'm just not going to. Instead, let's scroll back down to get some clean space. And let's use this equation to our advantage. Write the equation of the line which passes through the points -3, 1 and 4, -2. Now, in order to write this equation, we need to make a choice. One of these points is going to be x0, y0. The other one is going to be x1, y1. And at first glance, it will look like that choice matters, but it actually won't. So I'm just going to choose arbitrarily. Let's make this first point x0, y0. Let's make the second point x1, y1. It will all work out the same. And one of the things you saw in the proof I just did is that no matter which order you set the subtraction, calculating the slope will give you the exact same value. So m is y1 minus y0, so that's -2 minus 1, over x1 minus x0, that's 4 minus -3. So this is going to be -3 over 7. Had you set the subtraction up the other way, you would have instead ended up with 3 over -7, which is the exact same number. Then with that, we have that y minus y0, which is 1, is equal to m, which is -3/7, times x minus x0, which is -3. And if we had chosen the other value for x0, y0, you would have instead ended up with y plus 2 is equal to -3/7 times x minus 4, which certainly looks like a different number. And so that's what we want to look at next. Just like the standard form that we started with, the point slope form of a line is not unique because there are infinitely many points that the line passes through, and you can choose any of them to be your starting point. And so what we usually do is take a couple of steps of rearranging things. right? Distribute the -3/7. We got a whole bunch of minuses, right? Minus, minus, minus is minus there. And then add 1 to both sides of the equation. -9/7 plus 1 is -2/7. And you can verify for yourself that if you had taken those 2 points and named them in a different order, when you get to this version, you would get the exact same thing. Right. In your previous study of algebra, you have probably learned that this is called the slope-intercept form of a line. The slope-intercept form of a line is very useful, very important, because it is unique. There is exactly one way of writing the equation of a line in slope-intercept form. And so whenever you have to write an equation of a line, generally speaking, the goal is going to be do some work, get it into slope-intercept form. That way there is exactly one right way of doing it. And so to wrap up for today, here's another similar problem for you to try on your own. I would like you to write the equation of the line which contains the points 4, 3, and 8, 5. Looking ahead, I mentioned earlier in this video that writing equations of lines is going to be something we look at quite a bit throughout this course. This problem involves the simplest case of how to find the slope of a line. We're going to establish in a couple of weeks another tool for finding the slope of a line that is far more powerful, far more complicated, and going to be something we use very extensively. So the first step of finding the slope is going to change, but the second step of finding a point the line goes through and using point slope form to write the equation is going to be exactly identical. For now, take a look at this problem, see what you can do with it, and I'll see you in the next video.